Hello friends, today we will learn about Bayesian update of normal distribution and we will consider a case of known variance. Let's say we have some data. So data vector D, that is x1, x2, and this goes up to xn. Now we can use this data to plot the histogram. So this is shown here. So let's say we have plotted the histogram for this data set. Once I have this histogram, we can also plot or we can also fit a distribution. Let's say in this case we fit a normal distribution. So this is a normal distribution. Now if you remember, there are two parameters in case of normal distribution that needs to be estimated, and in this case parameter is mean and a standard deviation. So for normal distribution we require two parameters, that is mu and sigma, and corresponding probability density function, that is the equation for this curve, can be written by this formula. So we said if I have a normal PDF, it requires two parameters. One is mean and another is a standard deviation or variance. Basically, variance is a square of the standard deviation. So we can perform the Bayesian analysis assuming that mean as well as variance both are unknown. We can also perform the Bayesian analysis assuming that one of the parameter is known. So let's say in this case we will assume that a standard deviation, that is sigma, is known. So this is what we were saying, that these two parameters can be estimated once we have the data available, and for simplicity we will assume that sigma or a standard deviation in this case is known, and we will perform the Bayesian inference, that is Bayesian estimation of mu. So we will estimate, so Bayesian estimation of mean, that is mu. So we have only one parameter now. So originally there were two parameters and we are assuming that one parameter is known. So we have to perform Bayesian inference only for mean. So now if you remember, in Bayesian inference we require two things. One is prior and another is likelihood. So if I know these two quantities, we can calculate the posterior distribution. So this is posterior. Of course, in this case, we also have to multiply by the normalization constant k. So I am assuming this constant is known, or we can also write posterior distribution is proportional to prior times the likelihood. Now let's say I have the data, any data x1 follows the normal distribution. So what I am saying, x1, x2 or xn all are having same distribution, and that distribution is normal distribution with mean mu and variance sigma square, where sigma square is known. So data is following this normal distribution. So I can write basically PDF, probability density function, for each xi. For example, if I write for xi, I can write, I have to simply replace the PDF in place of x with xi, and then I can get the PDF for the xi. So as I was saying, if you want to update mu in terms of Bayesian manner or Bayesian approach, you need to have two things. One is likelihood function, and you have to know this prior function, and then if you multiply, then you can get the posterior distribution of mu. So this is the prior distribution of mu, and this is the likelihood function corresponding to mu given the data, and this is the posterior distribution. So now we'll discuss the three things separately. So first we'll calculate likelihood, and then we'll calculate prior distribution, and then finally we'll see how the posterior distribution looks like. And we already said the data vector contains x1 to xn, and this all follows normal distribution. So now we know the distribution for xi, and then we can calculate the likelihood function. So if you remember, likelihood function is nothing but product of fx1, fx2 and fxn, and each are having normal distribution. So basically I can write product of fxi, and xi is nothing but a normal distribution. So same thing is written here, and I goes from 1 to n. So this function can also be written here, same thing. So this is I is equals to 1 to n, and other parameters are same. Now if you look this term or here this term, if you see this function is quadratic in mu. So if you expand this becomes xi square plus mu square minus 2xi times mu divided by 2 sigma square. So this function is basically quadratic in mu, and this is also an exponential function. So we generally call this as a exponential quadratic. So likelihood function is a exponential quadratic. Now let us discuss about the prior. So before discussing the prior, I have a question, and this question is, what prior I should take so that the prior and posterior has same distribution. So what I want prior and posterior having the same distribution. So what should be the condition on prior so that final posterior distribution and the prior distribution is same? So if you will think a little bit, you will see this. So this is the posterior distribution, that is the prior times the likelihood, and I am saying this likelihood is exponential quadratic, and you also need posterior distribution that is exponential quadratic. So what kind of prior we will take? Of course, if I take an exponential prior, so what will happen if I multiply prior and likelihood? So product in case of exponent, it will become sum. So if I take exponential quadratic here also, so in that case, this is exponential, this is exponential. So whatever the term here I have, that is the quadratic term, and whatever the term I have here, that is quadratic term, let's call this is a quadratic 2 and this is quadratic 1. So this is q1 and this is q2. So if I multiply this will come quadratic 1 and this is quadratic 2. So finally the posterior distribution will also be exponential and it will contain a quadratic term. So this will become a exponential quadratic. So this means if I take a prior distribution of exponential quadratic form, the corresponding posterior distribution having the same kind of distribution or same kind of function. So such priors are often called conjugate prior. So what is the conjugate prior? So conjugate priors are the priors in which case the prior and posterior distribution has similar form. So let us consider prior for mu, that is the normal, because I need exponential quadratic. So mean is basically having a prior distribution of normal, and that is having mean of mu naught and variance of sigma naught square. So mean follows a normal distribution with mean of mu naught and variance of sigma naught square. In other words, we can write PDF for the prior distribution or for mu, that is this function. Only thing is in place of x, now I have replaced this with mu because this is a probability density function for mu and the corresponding parameters are mu naught and sigma naught. Of course, in both cases, these parameters are known. So mu naught and sigma naught in this case is a known parameter. So now I know my prior distribution and likelihood function, then I can calculate posterior distribution, which is normalization constant times prior times likelihood. So let us write, so this is the prior for mu, this is the same thing that we have here. Now this is the likelihood that I have already calculated earlier, and this is from I is equals to 1 to n. So product of all these terms, all these fx, that is the normally distributed fxi, and we have to multiply all this. Now let us take this k and this constant here. So if I multiply all this, I can have another constant. Let's call this constant as k dash. So now I will left with this exponential term and this exponential term, and product from I is equals to 1 to n. Now if I sum this term, so this will go exponential and this will sum, plus this will also be sum. So this is minus half of this term, and this term is same as here, and this product if goes power, then it will become sum of that. So that is this thing. So same thing can also be written as like this, that is k dash. If I take minus half common, then this will become mu minus mu naught divided by sigma naught and raised to the power 2, and here I will have a plus sign because I have already taken minus sign in the beginning. So this is the expression for posterior distribution of mu, and this has to be a exponential quadratic or a normal distribution, because we have taken prior as normal distribution and my likelihood is also normally distributed. So my posterior distribution has to be a normal distribution. So we can assume that this posterior distribution follows a normal distribution, and the parameters for that is mu dash and variance is sigma dash square. So what is the idea in this case? Basically we want to calculate, or we want to estimate mu dash and sigma dash by equating two expressions. So let's see how we will do that. So my mu follow a normal distribution, then I can write PDF for mu is like this. So now my question becomes simply calculation of, so we have to determine the value of mu dash and sigma dash in terms of prior mean mu naught and prior variance sigma naught square. So basically if you see this equation, let's call this is equation 1, and this equation, that is equation 2, these two equations are identical. So we will use this fact that 1 and 2 are identical. So basically we will expand and then we will try to equate some of the coefficients. So let's say this term that is inside, so we will try to expand this term. So let's call this term as a. So let's say we can expand a and then we can equate with equation 2. So a term is nothing but I have mu minus mu naught sigma naught raised to the power 2 summation I is equals to 1 to n, and x minus, that is xi minus mu divided by sigma square. So this is the term that you have in equation 1, that is term a. Now if I expand this term, I will have, if I take mu square, then I will have 1 by sigma naught square plus, now this term will be n by sigma square. So this term, that will be mu square, and if I take summation, then it will be 1 plus 1 n times, then mu square if I take common, so this will become n by sigma square. And other term we will have minus 2 mu naught by sigma naught square, and this plus summation of xi divided by sigma square. And other term we will have, that is mu naught square divided by sigma naught square plus summation of xi square divided by sigma square. Now similarly, the inside quadratic term we can also expand for equation 2. So basically in that case this term, so I have to expand this. So let's call this term as b, and then we can expand b. So b I have, that is mu minus mu dash sigma dash square. So this becomes mu square divided by sigma dash square, mu dash square divided by sigma dash square minus 2 mu dash divided by sigma dash square. Now we can equate the coefficients, that is coefficients of mu square and coefficient of constant term and coefficient of mu. So if I equate the coefficient of mu square, and then we can get 1 by sigma dash square is equals to 1 by sigma naught square plus n divided by sigma square, or I can write 1 by sigma dash square is equals to, I can take LCM here, and then this becomes sigma square plus n times sigma naught square, and we can write this term simply sigma dash whole square is equals to sigma square sigma naught square divided by sigma square plus n times sigma naught square. So now basically we have calculated a standard deviation for posterior distribution. Now let us equate coefficients of minus 2 mu. So we can equate coefficient of minus 2 mu. And if I do that, I will get mu dash divided by sigma dash square is equals to mu naught sigma naught square plus summation of xi divided by sigma square. Now if you calculate this, this will be sigma dash square, and then I can take LCM here, that is sigma naught square sigma square. So mu naught sigma square plus summation xi sigma naught square, and we already calculated sigma naught square in the previous case, so we can plug that value here. So this is sigma square sigma naught square, that is the value of sigma dash square that we calculated in part 1, that is equating the coefficient of mu square. This multiplied by this term, so mu naught sigma square plus summation of xi sigma naught square divided by sigma naught square sigma square. So this term cancels out basically in that case. So finally we will have mu naught sigma square plus sigma naught square summation of xi, and this divided by sigma square plus n sigma naught square. So we can further rearrange this term. If I rearrange, then I can write this is sigma square n sigma naught square, and this times mu naught plus this is sigma naught square divided by sigma square n sigma naught square times summation xi. So summation xi is related to sample mean. So if you remember, we can write sample mean is nothing but summation xi divided by n. This means summation xi is n times x bar. So if we plug this value in this equation, we can write this plus, and in this case this will simply becomes n times x var. So I can take n inside also. So we can write n inside. So this becomes sigma square n. So now if you see one important point, this and this, if you sum, then this will be equals to 1. And this is prior mean. So what was that? That is prior mean. And this is nothing but sample mean. And this side we have, that is the mean of posterior, so that is mu dash. So this is my posterior mean. So basically posterior mean is some fraction times prior mean plus 1 minus f times sample mean. Why I am writing 1 minus f? You can see if you sum this term and this term, sigma square divided by sigma square n sigma naught square, and both has the same denominator, so this will simply becomes n sigma square. So this is equals to 1. So that means my posterior mean is sometimes some fraction of prior mean and some fraction of sample mean. So one important consideration is about this fraction f, which is equals to sigma square divided by sigma square plus n sigma naught square. Now let's say if my data is very large, that is n tends to infinite. In that case, if n tends to infinite, this denominator will tend to infinite. This means my fraction will tend to 0, or 1 minus f will tend to 1. So if you see this, if my fraction tends to 0 or f tends to 0, this means this term has no meaning and this term will be 1. So this term will be 1. So in that case, mu dash is simply equals to x var, that is the sample mean. So one extreme. In another extreme, if my data set is very small, in that case mu dash is equals to mu naught. So this all makes sense basically. If you have a very large data set, my posterior mean is basically equals to the sample mean, because I am not going to rely on my prior information. It is also possible to derive we have enough the posterior distribution. But if I have very less amount of data, standard deviation in that case we have but that requires Markov chain Monte Carlo simulation, that is MC simulation. In practical, not we have some data in this course. Also some prior we can stop here. In that case, see you in the next video. Thank you. Both term will contribute to the posterior mean. So we basically said in this lecture or in this video that how we can calculate posterior mean that has a normal distribution mu dash and sigma dash, that is if I write in terms of variance, then sigma dash square. So once I know mu dash and sigma dash, I can plot my posterior distribution for mu dash and mu basically, and this is sigma dash. So this is the posterior distribution of mu once I know the prior distribution and the data that is giving me the likelihood. So in this lecture basically we learned about how we can calculate posterior distribution of a normally distributed data set when I know the variance term, that is the variance term is known.